Okay, I just want to give you a quick warning as we start chapter 7.3, using similar right triangles. It's going to sound more complicated than it really is. When you put the practical application to this into play, it's not as complicated as it really is. And I'm really going to try to make it a little bit more easy to understand. So just bear with me. It may be a little bit longer video. Make sure you watch it all the way through the end, and then we should be good to go. Okay. So the first thing you need to understand is that when an altitude is drawn to a hypotenuse, the two smaller triangles are similar to the original and each other. Okay, so if you look here, first of all, you need to remember that every triangle has three altitudes, okay? And that's when you take your angle, and what you essentially do is on that angle, you draw it from the angle to the opposite side and make it perpendicular, right? Okay, and so you're going to have three altitudes. Now here's the deal. We're going to use these altitudes, and when I do this to the hypotenuse over here, it's going to create this right triangle. And what you're going to notice is that you're going to have three similar triangles. Now let's take a look here. If you look at this here, this, and I'm going to change my color so you can see it a little better, is a right triangle right there. Okay? Since this is a right triangle, what you're going to find out is that this angle right here, angle B, is going to be congruent over here to this angle right here, angle C. Okay, think about this for just a second. These two angles right up here, ABD and CBD, they create a 90-degree angle. So they are complementary to one another. These two angles here, A and C, have also got to be complementary angles, because if ABC is a right angle, okay, so if this right here is a right angle, that means A and C must be complementary also. And so what happens is that you end up with these angles being congruent to one another because of the complements. So A is now congruent to angle DBC. Okay, so A is congruent to DBC. Okay, and angle ABD is congruent to angle DCB. And so now, since you have those angles being congruent to each other, using the third angle theorem, now you have similar triangles. And so now you have two similar triangles, and then of course they're similar with the big one as well. Okay, that just seems more complicated than it really needs to be. Okay, but it is. If you break it down and you really look at it, you'll be able to figure that out. Don't stress too much over that, though. All right, so let's take a closer look at this, okay? So, to me, the easiest way to do this is to break this up into three separate triangles. Okay, so you're going to have a triangle, and I'm going to make them smaller for space purposes. But you're going to have a triangle right here that is ABD, right? And here is your and again, it's not drawn perfectly, but that's your right angle. Okay, and then you're going to have a triangle right here. That is your DBC. And here's your right angle. And then finally, you're going to have the triangle, the big one, right here, where that's the right angle. And then you have, it's A, B, C. So to me, if you break up these three triangles, it's going to be a lot easier to see. And what you're going to find out is that this angle right here, from that first picture, is going to be congruent to this angle here. This angle here, angle A, is going to be congruent to this angle here. And of course, that's angle A also. So angle A is going to be congruent to itself. So that's kind of a better way to look at this picture. And here's C again. I didn't put those in there. So there's another way to look at the picture so you can actually see all the congruence. But what you're going to see now is they're all congruent to one another. Okay? And so what happens is that makes them all similar. So let's take a look. Okay, so now you can state that triangle ABC is similar to triangle ADB. Okay, we're going to make 3 similarity statements. Excuse me, sorry. And then you're going to have triangle, pen's not working. Then you have triangle ADB. It's similar to triangle BDC. And then you're going to have triangle ABC is similar to triangle BDC. Now you're going to find out some interesting things about this, okay? And again, you can now see these triangles, these 3 triangles that we're talking about represented above, okay? Now, look at ABC and ADB, okay? So let's take a look at ABC and ADB. So we're looking at these 2 triangles right there. What side do they have in common? Yeah, AB is in both triangles. Okay, so AB, segment AB, is in both triangles. Now, that's going to be relevant because, well, actually, we're going to pause on that for just a second. I don't want to go into too much detail on that yet because it's going to be complicated. But notice AB is in both triangles. But here's the key thing you need to understand. And I'm going to change this color here. I'm going to change this. And this is, if you look at your right triangle, what is AB represented here? That's your hypotenuse. That's C, right? And so if you want to label this leg A and this leg B. Now, let's go ahead and identify those on all the other triangles as well. Now here, remember, the hypotenuse is always across from the right angle. So let's do those first. So here, it's across from angle D. Here, it's across from angle B, right? So then, across from the one segmented congruent angle, so angle angle A over here in this first one is leg A. Now here is the similar side, the corresponding side. And here over here, across from A is the corresponding side. Now in the first triangle, across from the B angle is that little b. But on this one, it's going to be across from the C, because those are the congruent angles, right? And then across from angle C, again over here, is going to be that little b. Okay, now if you look closely at those, you're going to see how they match up. So AB in the triangle ABD, okay, in this triangle here, AB is the hypotenuse. But AB in this triangle here is simply a leg. So when you write a similarity statement or when you write a congruency statement, you're going to notice you can't put those together. So when you're doing a proportion, you won't be able to put those together. Okay, and we'll talk more about that in a second. Let's go to the next one. What do they have? What does triangle ADB and BDC have in common? Yeah, BD is in both. But again, in the first triangle, BD is leg A. In BDC, which is that middle triangle, BD is leg B. So they don't go together. And then let's look at the last one. You have ABC, triangle ABC. So that's the big one on the end. That's the big one on the end. That's this one. Is similar to the middle one, BDC. Okay, what do they have in common? They both have BC. So BC is in both. And I apologize for my terrible handwriting on this thing. Okay, now, here's what's going to happen. Since AB, I'm going back to the first column here, since AB is in both, AB is the geometric mean. Okay? Because AB is in both, it's the geometric mean. Because BD is in both, BD is the geometric mean. Wow. And then because BC is in both, you should have gotten the hint now. BC is the geometric mean. Should have seen the pattern. Okay, now let's investigate and let's explore that a little bit because that's what gets complicated. In order to explore that, we need to go back to geometric mean and then we'll go back and look at our angles again, okay? So, if you remember geometric mean, okay, in the book it shows you that A over X is equal to X over B, and therefore it yields X times the square root of AB, okay? Now, don't worry about this part for now. What we're going to really key in on in this particular section is the fact that two numbers that are the same are being multiplied together. And since two numbers that are the same are being multiplied together, that's how you end up with the geometric mean. So if you can recreate that proportion, you're going to have a geometric mean. So let's go back for just a second to triangle ABC similar to triangle ADB. Okay, so we're looking at ABD and ABC again. And I brought these diagrams over to help us look at this. If I was to set up a proportion using corresponding parts, okay, that means I want to set up C over C is equal to A over A, which is equal to B over B, something like that. If I wanted to set that up, and I'm not sure why I didn't put it in alphabetical order, but if I wanted to set that up, then that's how I would set up a proportion. Okay, so let's look at that. Let's start with AC. Okay, so looking at our first triangle, our quote unquote our big triangle, let's look at AC. So I would set AC, what does it correspond to? So what is this side right here correspond to in triangle ABD? Yeah, that's the hypotenuse, which is AB, right? So AC is over AB. And if I'm creating my proportion of my ratio, what I'm going to find out is if I go ahead and put that to over here, side AB, in my big triangle, okay, what does that correspond with in ABD? Well, that was side B. So side B over here is AD. And so now you can notice very clearly that ABs are going to be multiplied together. And it almost looks very similar to our geometric mean up here, right? That's why when you're doing this right here, when you have two triangles that are similar, but they form just two similar triangles, the side that they have in common, and in this case it's going to be an altitude they have in common is going to be the median each time. Okay, so that way you don't have to calculate it, you can just go ahead and figure it out that way. It's always going to be the median. Okay, hopefully that's more simplistic and not too terribly confusing. And that will work on all of them. Okay, if I did that for each one of them, you're going to find out I could set that up each way. So the side that shows up twice is going to be the geometric mean. And the thing that's important about this is, to be honest with you, you're not going to use it next year, or you probably won't ever use it again outside of this class, but it could. It's a possibility that it could show up on your SAT or your ACT. Okay, so that's why it's something that you really need to actually learn and kind of put in that file storage, if you will. Okay? Now notice, if I do this, I'm going to end up with 3 geometric means. If you go back here with these 3 triangles, I have 3, 1, 2, 3 different geometric means, right? So I can have 3 different geometric means. You just got to make sure you're paying attention to which one you want to use. And they all, if you notice, all the common legs, all the geometric means come out of the right angle. Because remember, this was the initial right angle right here, right? Of the original triangle. And so look, what are my geometric means? The first one is AB. The second one is BD. And the third one is BC. Okay? That is not by coincidence. All the geometric means will come out of that right triangle, or that right angle on the big triangle. Okay, let's move on. Hopefully you're not overly confused. Okay, here we have a guy looking at a flagpole. We want to know how tall the flagpole is, okay? And so according to our diagram here, the guy is about, from where his eyesight is, it's about 6 feet high. Okay? He's roughly 10 feet away from the flagpole. And that 10 right here will represent if he looks straight on at the flagpole. Okay, and so what that's going to do is that's going to create you a right angle here, and of course a right angle here. And then he's got another line of sight that goes upward, okay, that looks at the top of the flagpole, and then another one that looks at the bottom of the flagpole, and so that creates another 90 degrees. And there's your other right triangle. Okay, and so now it's very similar to the diagram that we just saw at the very beginning of this particular unit. You have an altitude going from the right angle to the hypotenuse. And since you have the altitude going from the right angle to the hypotenuse, you've now created similar triangles. And so what I want to do is figure out how tall the flagpole is. So I'm going to need to set up a proportion in order to figure that out. Well, in order to figure that out, I only have 2 numbers, right? You guys are used to having 3 numbers, like 3 over 6 is equal to x over 4, right? That's a proportion that you're familiar with because you have 3 numbers, you just need to figure out the 4th. In this case, unfortunately, you only have 2 numbers. But what you should have just learned from a second ago is your geometric mean is going to show up twice. Now, which one is my geometric mean? And remember, I said all of the means, the geometric means, come right out of the right angle. Okay, well, that means it's either got to be this one right here, This could be a geometric mean, or this one that we've already drawn could be a geometric mean, or this is a geometric mean. Remember, geometric means show up twice. So what geometric mean am I going to use? Well, obviously I'm only given one, so I'm going to use this 10, right? Now here's the deal. Let's put this together in a proportion. So let's break these up into some triangles that we can work with. So here, I have a right triangle. I'm simulating that bottom right triangle. So this is 10. This is 6. Okay? Now I want this height right here, right? I want to go from here to here. Right? And so that means at the very least, I need this side right here. So probably my best bet then is to go ahead and use this triangle here. I'm not going to attach them. I don't want to confuse you. So the triangle that's just standing up like this, where your right angle's right here, okay, and this is your 10. All right, now let's go ahead and set up a proportion. Okay, another way to make this easier for those of you who don't see this right away, which is understandable, let's set up our ABC. I'm going to make this one here, B here, and C there. Over here, I've got A here, B here, and C there. So if I set up my proportion, okay, the right way, what I'm going to notice is that 10 over here goes with B. I'm sorry, 10 in this triangle, let me give you a pointer. This triangle here is my A value. So I can put it over the A value in this triangle here, which is 6. I can set it equal to the B value here, which we don't know. And that's what we're really looking for, is that B value. And the B value over here happens to be 10. So now I've set up a proportion. In this particular case, which doesn't always happen, I'm not using a hypotenuse at all, right? So basically, essentially, I'm leaving the hypotenuse out, okay? So I can now solve this proportion, and I'm going to end up with 100 is equal to 6b. If I solve that, I divide both sides by 6, and I end up with 16.7 is equal to b. Now b is only this part right here. So to answer my original question, how tall is the flagpole, I need to do 16.7 plus 6 in order to get my final answer. Which of course comes out to, 22.7. And so my answer is 22.7. Now another quick shortcut way to do this work down here, I'm going to erase this for just a second. Another quick shortcut way to do this is knowing what I know about geometric means and taking away my arrows and all this other fancy stuff here. To be honest with you, all I really have to do is say, okay, basically 10 is being used twice. 10 shows up in this triangle and this triangle. So I'm going to put a 10 here equal to a 10 here. Okay, I have one other number, which is 6. it doesn't matter where I stick it, and then I can put x there, and I'm still going to get the equation the same. And that's kind of a shortcut, because I know that geometric means are going to be multiplied against each other like this right here. These two 10s across from each other. And so that leaves a 6 as the odd man out as the number that I'm going to use to divide, and that's going to give me the answer. So that's also a shortcut method to look at it. But again, you want to make sure, if you're good at proportions, you can do this. This is not that difficult, okay? But the hard part is actually seeing the triangles. I think that what's going to take more time and more time-consuming part is the fact that you're going to have to be able to see where the triangles correspond to one another. Okay, hopefully you guys are understanding that to some degree. All right, let's look at our last example. In this case, it's asking me to find the altitude to the hypotenuse. Okay, so essentially what I'm looking for is from my right angle to the hypotenuse. And this, of course, will create a right angle. Okay? So I need to find this value here. Okay, so again, I'm going to use a couple things. I need to go ahead and set up a proportion. Okay, so now I know, because I just did this altitude and based on what I learned at the very beginning, I know I have similar triangles. So this big triangle, and if I want to do this to break it down to make it a little easier, I have a triangle here. This is my big triangle. There's my right angle. This is 4 square roots of 13. This is 8. This is 12. Okay, and I'm going to go ahead and use this triangle here in order to solve. So to set this triangle up, it's going to look something like this. And you have your x here and 8 here. And this is some portion of 4 square roots of 13, which is not going to be relevant. Now, here's the deal. We're looking for the altitude now, which means it's going to be the geometric mean, right? Because remember, we said the geometric mean, just kind of a review, the geometric means come out of here, here, or here. And the geometric mean is the one that shows up twice. So I can't just throw a number on there twice. This is actually going to be a normal proportion. So if I just understand that the key to getting this problem right is understanding the triangles are similar and then setting together the corresponding parts. So, for example, I'm going to go ahead and set up my x value. What part does it correspond in this triangle here? Hopefully you said 12. And it does correspond with 12. It's going to be equal to eight in this triangle. Again, we're looking at the small triangle on top. What does 8 correspond with? Well, that's the hypotenuse, right? Because this is the right angle. It's across from the right angle. That must be the hypotenuse. Okay, so this is the right angle over here. Across from it, the hypotenuse is 4 square roots of 13. So here we actually have a normal proportion. And so all we have to do is multiply them together. So you got 8. So then you have 96 is equal to 4 square roots of 13 times x. And if you work that out in your calculator, divide both sides by 4 square roots of 13, you're going to get x is equal to 6.7. Again, this is actually, in my opinion, an easier problem, but you have to understand how to set up the proportion. If you're good at proportions, again, I said this earlier, if you're good at proportions, this will be no problem, this particular problem right here. Okay, but you don't want to get it confused with the other problems where we are repeating the geometric mean. In this case, we use several of the different sides. Okay, it's not that challenging. You just got to make sure you set it up right. Okay, and again, hopefully, I know that was a little complicated and confusing, but hopefully you understand. If you have any questions, write it down. Make sure tomorrow you take a lot of time working through these problems. And if you don't watch the video, you're not going to hear this anyways. But again, come see me if you have any questions.